Hello everyone, this is the BK Math YouTube channel. This lecture is concerned with applying calculus in the context of a vector field. I think you have most of you familiarized with what vector and scalar mean. I think it was exceedingly elementary. I don't want to remind it here. Let me remind you simply what scalar fields and vector fields is generally. What scalar field and a vector field. Before we talk the distinction between vector field and scalar field, I think it's better to remind what fields are generally. Fields, or simply a field, is a continuous function that returns a number or set of numbers for every point in space and time. But here we will deal with basic flavors of fields like the scalar field and vector field. Scalar field f of x, y, z, and t returns a single number for every point in space and time. It just gives us a single number for every point in space and t and time we mean. Whereas a vector field, big F of x, y, z, t returns a vector for every point in space. And just readily visualize it as a field of arrows here. That's the distinction between the vector and scalar field. Conveniently, this is the notation for vector fields generally. So scalar field, something that has a particular value at every point in space. We have instances here: temperature, density, salinity, porosity are examples of the scalar field, whereas velocity, electric, and magnetic fields are some of the vector field. The rationale behind the discussion of the vector field is a vector field has many important applications, as they can be used to represent many physical quantities. The vector at a point may represent the strengths of some forces like gravity, electricity, magnetism. Okay, like here we just mentioned the instances. So that it's crucial in nature to deal with the vector field for various reasons. Now, having this in mind, let's just move to the vector calculus. What vector calculus is? Vector calculus here in our section, we just want to talk about limit, derivative, continuity, integration of vector as a function women. That's why for convenient we just start from the definition what vector valued function is. It's just a rule that assigns to every point because it's just a function. That must be a mapping or a rule that assigns to every point in R a unique vector in Rn. That's in n dimension here. So we have R of t is either you can use f of t, g of t in 2 dimension, that is 2-dimensional vector valued function, or the 3-dimensional vector valued function is f of t in the I plus j of t in the j plus h of t in the k, either in the ij component or in the component wise here. You can rewrite alternative notations here. Maybe I think it might be possible to represent with this ijk component or with this form, with this express whole. So that the two-dimension vector calculus, vector valued function, and the three-dimension vector valued function women. So it's just a rule that assigns to every point t in the real line a unique vector in Rn. So it's just a function whose domain is the set of real numbers women. Domain in the set of real number, and whose range is set of vectors. So whichever you're playing inside here, either in 2 or 3 dimension, just turns a vector valued function in both cases. So that, roughly speaking, vector valued function is a function whose domain is a set of real numbers and whose range is a set of vectors women. The range of the vector valued function R of t is a curve in R2 or in R2 women. So here conveniently we just noted as the R of t women here big, with the headed arrow to distinct from the scalar valued functions. But individuals, these are scalars. F, G, and H are scalars. R is a vector valued function, so that for every point t in R, a unique vector is given, which gives the vector function a vector valued functions here. As I told you before, vector valued function is a function whose domain is the set of allowable input values, any point, the real numbers, again whose range is the set of vectors That's why the domain of the entire vector valued function depends on the domain of individual components. Okay, domain of individual components Let's say if we have R of t, cos t, ln t, 4 minus t, square root of 2 plus 1. This is the vector valued function. We have cos t in the I, ln of 4 minus t in the j, square root of t plus 1 in the k. To identify the domain of this function, individual components must be defined for some value of t That's why cos t, we have to be study the behavior of individual functions here for simplicity. Just cos t is the domain of cos t is all real number. Ln of 4 minus t. 4 minus t must be positive to define the natural logarithm, because the set of input values here, 4 minus t should be positive, so that's why 4 minus t is greater than 0. Again, square root of t plus 1 is non-negative It might be a possibility to be 0 or possibility to be positive Okay, that's why t plus 1 is greater than or equals to 0. That means t is greater than or equals to minus 1. Again, this means 4 minus t is positive, greater than 0. That means t is less than 4. So we just combine it to have this form as a domain of the given vector valued function emanated from the definitions of individual components on some value of t That's why the domain of the entire vector valued function depends on the restrictions of the individual components Now we come to the vector calculus to deal about what limit, derivative, continuity, and integration. So for simplicity, we consider this vector valued function r of t, f of t in the I plus g of t in the j plus h of t in the k. We mean we have this vector valued function f and g or h are, this is in three-dimensional vector valued function. We may have two vector valued functions. That's just a matter of extension here that we need to do. So the limit of this vector valued function is just the limit of individual components we may. So where we compute the limit of the vector valued function, it's just component-wise limit we may. Limit of f of t in the I plus limit of g of t as t tends to a in the k plus limit of h of t as t tends to a and the k. Since f, g and h are scalar valued function, then the limit, the computation of individual limits are likely with the computation of limit of scalar valued functions you have seen so far in calculus. Okay, as any function f, g, so that you may use the property, basic property. Okay, we have seen constant multiple rule, the sum rule, the difference rule, the product rule, or the power rule. Any forms that you have been addressed could also work as for such functions due to the scalar value of this individual functions here. The same is true with the continuity of a function, a vector valued function at a single point A. Then it's just continuous if this condition satisfies. In a more compact form, you can be decomposed in three parts. One, r of a is defined. Again, the limit of r of t as it tends to a is exists. And finally, this must be equal. Existence of the limit, defineness of the given vector valued function at a. But in a concise form, you can say that if limit of r of t as t tends to a is r of a, then the given vector valued function is continuous at a we may. So that keeping this in mind, we can solve this problem. It's just a straightforward from the definition. Okay, good. All right. Given r of t, we have 2 areas t in the I plus t areas t in the j plus ln of 1 minus t in the k. Then we are asked to find limit of r of t as t tends to 0. Again, when does this vector valued function is continuous? So by definition, the limit of the entire vector valued function is just when to compute the limit of individual components, that's component wise we adopt the limit for individual components here for simplicity. So limit of 2 raised t in the I plus limit of t raised t in the j plus limit of ln 1 minus t in the k as t tends to 0 in both cases. Using constant multiple rule, you can use this direct substitutions here and exponential. So 2 limit of e raised to mean 2 e raised 0 with as t tends to 0. That's 1. Again, limit of t e raised t as t tends to 0 using product rule, just to obtain it 0. Again, limit of ln of 1 minus t as t tends to 0 mean if you make as t goes to 0, 1 minus t tends to 1. So ln of 1, which means 0. So we have 2, 0, 0, 2 in the I component. Again, 0 in the j component, 0 in the k component we mean. So this is the limit of the given vector valued function. At what value of t does this vector valued function is continuous? in here we have to look at individual scalar valued functions here for the component, where each individual components are defined here. E raised t is defined everywhere, so exponential functions are continuous here. This exponential function with no restriction. We mean similarly for here t e raised t, but when you come to ln of 1 minus t, this ln 1 minus t is defined or having meaning for when 1 minus t is greater than 0. Even in 0 it could not be defined, that's why 1 minus t should be greater than 0. We mean t is greater than 1, so this function is just continuous for all t in 1 up to infinity, just ranges from 1 to infinity, we mean. Similarly, for the other calculus, the derivative is just defined using the concept of limit, or using the approach of limit. More analogous with the functions for scalar valued function, derivative of any function at any point x you have seen. So it's just analogous with the vector valued function here. So that it's just defined as a limit at h tends to 0, r of t plus h, an increment here, minus r of t over this small increment here. So provided this limit is exists, to have the differential, to say the given vector valued function is differential. Otherwise, if the limit fails to be held, the vector valued function is not differential, we mean. So that just completed through this definition. But for simplicity, to apply the basic property, we have r prime of t is f prime of t, g prime of t, h prime of t, having r is f, g, h in the ij components respectively. So the derivative of the vector valued function is a component wise, like we did in the limit approach. So for the first case, in the previous case, we have r prime of t mean making differentiation of what the function was, because this was the function here and here, because our function was this. If you make differentiate this differentiation is 2, e raised t, again this differentiation is 1 e raised t plus t e raised t using product rule. Again, this is ln of 1 minus t, mean differentiation is 1 over 1 minus t. Again, differentiation of 1 minus t, we mean minus. So finally, we get this. I think it's extremely elementary to make differentiation. Revision of the scalar valued functions, the only thing is being as a vector we treat. Let me remind you the properties of derivative, basic properties of derivative here. Suppose u and v are differentiable functions. Again, c is the scalar and f is a real valued functions. Then these properties are holds true. The following properties are holding true. D by dt of constant multiple times u is, we use the constant multiple rule. Again, d by dt of the u plus or minus v mean d by dt of u plus or minus d by dt of v. Again, the dot product is the same thing. U dot v derivative of the second function plus the derivative of the first function dot product with the second function with no derivative. Similarly, we have a cross product. D by dt of u cross v is u dot, the derivative of u cross v plus u cross v derivative. again d by dt of f of t u of t mean f of t is scalar valued function, then you can use dice that like the ordinary product rule, f prime u plus f u derivative. The same is true again. If we have u of f of t composite function, we have f prime, the derivative of the inner function, times outer derivative of outer function evaluated at f of t women. So those are the basic property you can prove using the definition. Again, with the help of this property, as an assignment, you have to try this problem. I think the solution of the problem is just released in the next video. If you subscribe it, then you will obtain the solution directly in the next video. Besides this, we have also another calculus, that is the integration for a vector valued function with the same concern of the vector valued function. The vector valued function r is definite integral here from a to b of r of t mean term-wise integration. Okay, individual components should be integrated from a to b. The other thing is lateral. I mean, from a to b f of t, you have some value again from a to b g h with the other values respectively. Let's say if you have 2 in the I plus 3t in the j, we made components wise integration here. Integration of t mean using power rule to square over 2 plus integration of this mean to cube it over 3 times 3 is 1. That's why you just finally assign specific value at 3, then at 2, then you obtain this algebraically. So that while you are calculating or computing the definite or indefinite integral of the vector valued function, like you did in integration, the ordinary integration for scalar valued function, you can apply the mechanisms or how we tackle the integration with various methods remain possible. So it's just pretty easy to understand how calculus is applying calculus in the context of vector valued function women or a vector field. Now we move on curves, arc lengths and tangent. Consider a vector function or a vector valued function r of t, where f of t, g of t, h of t is this. The set C, this is the characteristic C of all points x, y, z, such that x of t, y of t, z is h of t, again y is g of t, is called a space curve. A space curve. Okay, so that there is a close connection between continuous vector function and space curve women here. The connection between this. So in here, this equation, parametric equation of C and T is called a parameter. The parametric equation of the given curve. We can think of this C or the characteristic C as a being traced by a moving particle with position at time t is f of t, g of t, and h of t women. Okay, by the positions f, g, and h. That's where we think C being traced by moving particle whose position is this. Thus, any continuous vector valued function are defined as a space continuous, as a space curve women. Okay, C, which is just traced out by the tip of a moving vector f, g, and h women. So if we think this curve, okay, if you think of the vector at the position, this is the vector at the position f, g, h, with their initial point in at the origin here, then the end points r of t, f, g, h, traced out as a curve in R3. We take constant arbitrary. Clearly, curves are traced out by the terminal points of the vectors formed by the final values of f, g, and h here. So this curve C is traced on the vector valued function we mean. So the curve C is just traced by a moving particle whose position at time t is f, g, and h. We mean essentially. Having this, we prosed the arc length of a curve. The arc length of a parameterized function. Sometimes it's useful to compute the length of a curve in space if the curve represents the path of a moving object. The length of the curve between two pointers may be the distance traveled by the object between the 2 points here. So the arc length of a parameterized function r of t, f of t, g of t, h of t is defined with this formula. L is from A to B, f prime of t square plus g prime of t square plus h prime of t square dt. Or since this r is here, this belongs to magnitude of r of t with the magnitude of r of t. That's why for simplicity we can use here either of the two formulas in finding arc length of a parameterized vector valued function in between 2 points here. Now let's develop the idea with the example. We have this: find the arc length of the curve r of t root 2 t e raised minus t when t lies in between 0 and 1. So we apply the definition. The definition was from A to B, magnitude of r of t dt. So we first find magnitude of r of t dt to apply, to compute this integration. A and B are from 0 to 1. A is 0, B is 1 in this case. So needs to compute the magnitude of r of t. It becomes like here, since r of t is square root of 2t e raised minus t, then making differentiation or component wise like we did before gives square root of 2 e raised t minus t we mean. So we have, it's just making the magnitude we mean because these are the vector. So that its magnitude is this square plus this square plus this square under the square root. That's why we got 2 plus e raised to t plus e raised minus 2t. This is that. This L is from 0 to 1. From A to B indicates from 0 to 1, since t lies in between 0 and 1, where our r prime of t is here. Okay, we have already obtained from the definition of what magnitude looks like. I think this integral looks very complicated. How can we solve it? How can we solve this? From 0 to 1, 2 plus e raised to t plus e raised minus t. Obviously it's just visible here, but you have to try by yourself how we compute this integration. We need to use a clever algebra. Okay, then this we just factor out e raised minus 2t from this, then factor, if you make expansion of this, just distributed here, it just wanna be gives 2 plus e raised to t plus e raised minus 2t, so that this can be moved out of the square root e raised minus t. Again, this will be written out here. That's why it can gives e raised minus t with this form, e raised t plus e raised minus t here. This is the integration, so that is very simple. It becomes very simple now. Now finally, e raised t plus e raised minus t integration is e raised t minus e raised minus t. t is equals to 1, t is equals to 0, so a raised minus 1. This is the arc length, so they have to be practiced the integration as well. Okay, let's proceed to the other ideas. In addition to the length, we would like to have idea of curvature for of a path. For instance, when probes are sent in outer space, engineers curse a great deal about how many times it must take since the impact of the fuel consumption. Before we look at on the curvature, but I think it's better to discuss about the tangent vector, given this is r prime of t, f prime of t, g prime of t, h prime of t. The distance from the component wise is called tangent vector. Again, the unit tangent vector means r prime of t over its magnitude. Okay, that's unit tangent vector. It has a vector that has its magnitude is 1 we mean. Now, the curvature k of t is defined as magnitude of t prime of t over magnitude of r prime of t we mean. Let r of t is here. Find the curvature of the path at time t. That's the fundamental question to be raised. How do we measure curvature? We want to measure the amount of a curvature changes direction. Since it's a measurement, it will a scalar value. The computation is very simple. It's just straightforward. We wouldn't want to measure changes in magnitude. We only want to look at the direction, because it will be the amount of 2t changes as we travel along a segment we mean. Amount of tt changes as we travel along a segment we mean. So at any time t, we have the definition of the solution for the curvature is t prime of t, r prime of t. We first find r prime of t using the derivative. Again, its magnitude is there. Again, t of t is r prime of t over its magnitude. That is, everything is very simple. It's just I skip a big chunk of this work. It's so simple. Therefore, our curvature becomes here. Okay, that says it's straightforward, very simple. I think it looks, sounds simple. So the curvature is half positive. That means at any time t, we are turning in the same way as we travel women. So curvature is very essential behind the idea of arc length women. So to find similar video, please do not forget to subscribe at the bottom.